This is your review for momentum and energy for physics. I'm going to cover both topics, including simple harmonic motion. First, momentum. Momentum is P equals mv. Momentum symbol is the P. Mass is, of course, m is mass in kilograms, and v is velocity in meters per second. Units for momentum are kilogram meter per second. Change in momentum is mass times a change in velocity, because the mass isn't going to change just because velocity changes. So any change in momentum is because the velocity changed. Impulse goes with momentum here too. Impulse is the force, external force, times the time interval that the force was exerted. Its units are Newton seconds. We talked about this in class with a lot of sports analogies. If you want the ball to go to really change its momentum in baseball, you would want to, first of all, swing really hard. That gives you a big force, and then follow through. So that gives you a big time interval for that force to be exerted. The longer the force is being exerted, the more impulse you have, and the more momentum will change, because impulse is change in momentum. I just wrote it in the form of m delta v. That's the form that you most often use it. But remember that m delta v is the same as delta p. So big impulse equals big change in momentum, and you can use that in calculations. That impulse has to be, or that force that causes the impulse has to be from an external force, not internal to the system. Conservation of momentum can be represented by momentum of object A plus momentum of object B plus or minus the impulse equals momentum of object A and object B after. So the left side of this equation represents the before situation. The after side represents the after situation. Again, that impulse would have to be an external force. So when we do a problem with a bullet being shot from a gun, the system is the bullet and gun. And even though they seem like they're one thing to begin with, if they are going to be doing different things on the after side of the equation, you want to treat them as separate objects on the before side of the equation as well. You had a homework problem where an object breaks apart, like firecracker. So you're going to treat those as two separate objects, even though they start off as one object. What are those two pieces doing before the explosion, and what are those two pieces doing after the explosion? That helps with those problems. Those momentums could be positive or negative, so make sure you are defining the system consistently, and the force must be external. So that could be friction, that could be somebody coming in and pushing, but if it's the bullet and the gun and the explosion is happening within that bullet gun system, then that is an internal force, does not count. You don't have to know anything about newtons or seconds in order to do conservation of momentum for the bullet gun system, or the firecracker exploding, for instance. Now energy, we have several forms of energy. The first is kinetic, 1/2 mv squared. So this means that because mass is always positive, and velocity, whether it's positive or negative, you're going to square it, so that is going to turn out to be positive. Kinetic energy is always positive. There is no direction associated with energy. It is not a vector quantity. Kinetic energy must be positive or zero, because of the way the equation is written. Remember, kinetic energy is the energy of motion. If the object is not moving, it has no kinetic energy. And no matter which way it's moving, all you care about for kinetic energy is how fast is it going. It doesn't matter whether it's going to the right or to the left or up or down. Kinetic energy is the same for same speed. The next one is gravitational potential energy, mgh. For gravitational potential energy, remember that the g that we're referring to here is acceleration due to m. Let's go back. M is mass in kilograms, the mass of the object. G is acceleration due to gravity, so on Earth, 10 meters per second squared. You don't need to put a negative with that. This mg is just kind of like when you're doing weight calculations. And then the h is the height above the reference level. You set the reference level wherever is most convenient for you. Generally, you want to make it the most convenient place, which is often the ground, or sometimes might be like the height of the table. If the object is just moving across a table, your calculations are a lot easier if you just make the reference level the height of the table. That way it doesn't change, and it's the same before and after. It's 0 before and 0 after. That way you don't have to account for, some positive potential energy to begin with and the same positive potential energy to end with. So you choose wherever it's convenient for you. This theoretically could be negative, but I would not recommend it. Make your reference level something that's going to make gravitational potential energy either 0 or positive values. Makes it a little easier to work with. Spring potential energy is 1/2 kx squared. So the k is representing the spring constant, newtons per meter, how stiff is the spring. And then x is representing displacement from equilibrium, which again gets squared, very similar to the kinetic energy, the velocity and the kinetic energy. So even if your displacement from equilibrium is negative, you square a negative number, it turns out to be positive, so your spring potential energy will either be 0 or a positive value, not negative. The units for all of these are joules, capital J. Now work. Work is defined as F cosine theta delta x. The force and the displacement may be in the same direction, opposite directions, or theoretically at some angle. The cosine theta is taking into account if they are at some angle to each other. Here's our options. If F and delta x are in the same direction, then you have a positive number times another positive number, for instance, is positive. Or a negative times a negative is still a positive. The work is going to turn out positive. This means that the object will speed up. Whether it's speeding up in the positive direction or the negative direction, it doesn't matter. It's still going to be going faster. The cosine theta, if they're in the same direction, that's just cosine of 0, which is 1, so that's why that term goes away and it's just all positive. If F and delta x are in opposite directions, then your angle between them is 180. You're going to have a positive force, for instance, and a negative displacement, so that's going to give you a negative value. If F and delta x are perpendicular to one another, then the work is 0. Oh, sorry, let me go back to the opposite directions there with negative work. Negative work means it's slowing down. So it could be going in the positive direction and slowing down, or going in the negative direction and slowing down. Either way is what you'll get for negative work. Perpendicular means you have 0 work. The angle between them is 90, cosine of 90 is 0. So you have, did I say negative work? You have 0 work. You have 0 work done if they are in perpendicular to each other, 90-degree angle. So that means that if you are lifting up on an object and walking across the room, you are exerting a force and the object is moving through a displacement, but you are not doing any work on it. You might get tired, but you're not doing any work on the object because you are not increasing its energy in any way. So that's what work is doing, is it is either increasing or decreasing the energy of the system. So if you have an object and you lift it up, you did work on it, force exerted in the same direction as displacement, that did work on the object, and you increased its gravitational potential energy in that case. So that's what the work did, was increase the energy of the system. Simple harmonic motion is the last major topic for this test. So this was our cart moving back and forth on a horizontal surface. The equation representing there is Hooke's law. So that's Hooke's law equals negative k delta x. This can help us with the acceleration of the object. So remember, for simple harmonic motion, we're not talking about the object is just sitting there stationary. It is not in simple harmonic motion at that time. It's just sitting there. If, however, you go in and grab a hold of that cart and pull it to the right and let go, then it will oscillate back and forth, left and right in this case. In simple harmonic motion, if there's no friction, it will just keep doing that back and forth forever. You had to do work in order to get it going, in order to make something happen. Otherwise, there's just going to be a cart sitting at the spring in its unstretched position. It wouldn't be doing anything. Once you get it going, though, then you can track its movement left and right. So if the object is in a positive position to the right of 0, then because of Hooke's law, the direction of the force would be negative. A negative number times k is always positive, times a positive displacement, you end up with a negative force. And you know this from a spring. If you take a spring and you pull it to a stretched position, then it's going to be pulling back on you. It's trying to get you to go back to its equilibrium position, if you want to personify the spring. So a negative force means a negative direction for force means negative acceleration, because the direction of the force and net force and the direction of the acceleration must always track together. So that object has a negative acceleration. So if it's anywhere to the right of 0 in the positive position, then you will have a negative force, negative acceleration. If it is in the positive position and heading towards maximum displacement, then it's going to be having a positive velocity. If it's moving to the right, moving towards its maximum displacement, then so it's going to have a positive velocity moving to the right and a negative acceleration. It's going to be slowing down towards 0 speed when it's at maximum displacement. If it's in the negative position, that's going to be a positive spring force pushing you back towards 0. That's going to be a positive acceleration. So that means that you could be moving to the right. You could be in the negative place, but moving to the right. That would be a positive velocity and a positive acceleration. You will be moving towards 0, where you're going to be going the fastest, where the cart goes the fastest. Whenever it's at 0 position, the spring force is 0, there's actually no acceleration at that point. Spring force, there is no spring force when you are at, very briefly, at 0 displacement. So then we have this equation, x equals a cosine omega t plus phi. A is the amplitude. The units would be meters for that, or centimeters, some kind of distance unit. Omega is angular frequency, which is unitless. You have this expression, omega is 2 pi over the period. That must be unitless in there because the argument for cosine has to be unitless. You can't take the cosine of seconds, for instance. The omega is related to the period. So if I have a big value for the period, that means that I'm going to be dividing by a big number. That's going to be a low frequency. There's not going to be too many oscillations per second. Phi is the phase shift. We're not going to really work with phase shift, but you should know what that represents, that is that number that is inside the parentheses, it's in the argument, and it would be a left-right shift. It would kind of get you to the right starting point. We're not really going to work with it but in problems, but you should know what it represents, that it represents phase shift. Okay, so let's go to this graph that we talked about in class. You have a graph of position versus time. This position could be left-right position, or it could be up-down position, either one. It does not have to be, just because the graph looks like it's going up and down, that doesn't mean that the object is going up and down. It is going from a positive position through 0 to a negative position. Could be oriented horizontally or vertically. And then t is, of course, in time unit seconds. So the distance from 0 x position to the most positive x position is the amplitude. It's going to be the same value, if I had a better drawn graph, than if you went from 0 position to a negative, the most negative position. That's still amplitude. It's a distance that you are measuring on the position axis, so that's going to be meters, and that's what amplitude is. It's how far from equilibrium does the object ever get to, in the positive or the negative direction. But again, how far from equilibrium. The period is the time that it takes for any two repeating points. So in this particular example, the object starts off in the positive position, goes to the most negative position, and back to the most positive position. The time that it takes to accomplish that would be one complete cycle of motion, is the period. So if we have our object moving left to right, on a frictionless surface, once again, and you have taken the object, moved it to maximum displacement, and let it go. So you're picturing here that it's not just sitting there in stationary, I'm just taking a little snapshot of time. It's moving back and forth in simple harmonic motion. When the cart briefly passes through 0 position, delta x is 0. All of the energy that you gave it at the beginning, when you pulled it back and let it go, for it to oscillate back and forth, all of that energy has been transformed into kinetic energy. It is moving the fastest that it is ever going to move at that position. So at zero position, if you look on the graph that's above, zero position, that's going to represent where it's crossing the horizontal axis. That is where the slope of that position time graph is the steepest. It's moving fastest. So any of those positions, whether it was to the right and moving to the left, or to the left and moving to the right, it's still going to have the fastest speed, the steepest slope, either positive or negative. It's going to be going the fastest. The spring potential energy is zero because there is no displacement from equilibrium. Briefly. Then when it's at its maximum position, delta x is at its maximum positive position, the delta x would represent your amplitude. You could measure the amplitude for that. At that position, all of the energy is spring potential energy. There is no kinetic energy because the speed passes briefly through zero. All of the energy is spring potential energy because spring potential energy is 1/2 kx squared. The x is as big as that x is ever going to get. So all of the energy is spring potential energy. It briefly passes through a point of zero speed. So it has zero kinetic energy at that extreme point. That would represent the crest of that graph above. So any of the highest points. What's the slope at that peak? Zero. The slope of a tangent line would be zero at that point. Zero speed. Briefly. It's not going to stay there though. It's going to, that spring force that it experiences there is going to move it back. Make it keep going. If the object is in its maximum negative position, you have your delta x as a maximum negative. The delta x is still representing the amplitude, just on the other side of the equation, other side of the graph. All the energy would be spring. Kinetic energy is still zero. This would represent any of those trough positions where it has moved from a positive position through zero and made it over there to the left, where it's at its maximum negative position. The slope of a tangent line at any of those troughs in the graph above is going to be zero, zero kinetic energy. All the energy is going to be spring potential energy. It's not going to stay there. It's not going to stay at zero velocity. That spring force is going to push it to the right. So it's going to move back and do another cycle of motion. If you can follow this path, if you can match up the graph above with those positions and find where on the graph would the object be during any of those positions, how fast would it be going, what kind of energies it have, then you understand simple harmonic motion. You have a worksheet that matches up that we did last week that is trying to get at the same thing. If you go back and look at that same thing again after having practiced it once, start from nothing, you have it linked in your Connect assignment, and you'll be able to hopefully match those things up more quickly and more easily. Let me know if you have questions as you're studying. Good luck.